Welcome to the course Excelling with Mathematical Modeling. In my previous lecture, we have talked about this SI model. So today, we will talk about the SIS model. Now, to start with, a little recapitulation. So, this endemic, it is defined as usually a large short-term disease outbreak, and the outbreak will be called a pandemic if the disease growth is exponential, and it will be called endemic if it is consistently present but limited to a particular region. For pandemic, you can recall COVID-19, and for endemic, you can recall malaria, cholera, etc. So, these endemic models, they are primarily designed to explain and predict the spread of the disease and the way how you can control it. And the goal of the epidemiologist is to first to understand the cause of the disease and then to predict its course, and finally a way how to contain it or how to control it, including comparisons of different possible approaches. So, today our lecture will be on susceptible infectious susceptible model, in short SIS model. Now, we have seen in SI model that when a susceptible comes in contact with the infected person, they get infected. So, this is one class, the susceptible class, and this is the infected class. So, what is new in SIS? So, what we are assuming here that you can take the example of say common cough and cold. So, a person comes in contact with another person who is suffering from this cough and cold, and immediately he catches it. So, from the susceptible class, he moves to the infected class, and since he is moving to this class, this is negative, and the addition to this class, this is positive. Now, by taking some medicine which is easily available, you get rid of this cough and cold, but again you are susceptible. So, that is why I put a negative sign, that is you were infected, but then you recovered and you become susceptible again. So, from here minus alpha I, a part of it get recovered, but then again becomes vulnerable. So, plus alpha I. So, here what we are doing is that a susceptible person first gets infected, but he took some medicine and gets recovered and again move to the susceptible class. So, now you have this set of differential equation, and we will see that how your solution changes compared to the SI model. The initial condition S0 remains n, and we have one infected person. So, when you solve this differential equation, again we use the same technique. If I name it as 1 and name it as 2, 1 plus 2 will give me ds dt plus di dt equal to minus beta si plus alpha I plus beta si minus alpha I. So, everything cancels, this goes to 0, and this implies ddt of s plus I equal to 0. So, your st plus it equal to constant, and at t equal to 0, S0 is n, I0 is 1, implies constant equal to n plus 1. So, you get the relation St plus It equal to n plus 1. So, this is our 3. So, now you either eliminate S or you eliminate I from these two equations. I will eliminate I because, I will eliminate S because there is only one S here, and I solve for I. So, you have Ti dt, that is equal to beta Si minus alpha I. And obviously this alpha and beta, they are positive parameters, and so what I am going to do here is I will replace this S by n plus 1 minus I, because I have S plus I equal to n plus 1 and your S is n plus 1 minus I, so which I have replaced here. A bit simplification is beta n plus 1 into I minus beta I square minus alpha I. So, beta n plus 1 into minus alpha into I minus beta I square. Now, instead of writing this big constant again and again, I will replace it by some C and later substitute back this C, where your C is beta n plus 1 into minus alpha. So, I now have this differential equation to solve. So, I will use the separation of variables di dt, which is equal to take C minus beta I, and this implies di divided by I into C minus beta I equal to dt. So, I just take beta out. This is di by I beta C by beta minus I equal to dt. So, I have to write it in the form of the partial fraction. So, I will write this as 1 by I plus 1 by C by beta minus I, and if I do the LCM, I see that there is a constant C by beta. So, I put C here and it is all adjusted. So, if I LCM this I will give you a C by beta in the numerator. Already this beta is present. So, I multiply this by C and this by C, and hence this C will come here and this C by beta is adjusted here. So, now I will integrate. So, integrating this whole thing, I will get here ln I minus ln C by beta minus I. The minus sign is coming because there is a negative here, is equal to Ct plus constant. Now, we know that at time t equal to 0, I have I0 equal to 1. If I substitute here, I will get ln 1 minus ln C by beta minus 1 equal to constant. Ln 1 is 0, so my constant value is minus ln C by beta minus 1, which will be substituted here. And if you do that, you will get ln I minus ln C by beta minus I equal to Ct minus ln C by beta minus 1. So, I take the logarithm. So, this comes to this side and you will get ln I plus ln C by beta minus 1 minus ln C by beta minus I equal to Ct. This is ln I times C by beta minus 1 divided by C by beta minus I equal to Ct, and I can write I C by beta minus 1 divided by c by beta minus I equal to e to the power ct. I take the reciprocal because I have to find this I. So that will give me c by beta minus I divided by I c by beta minus 1 equal to e to the power minus ct. So c by beta minus I divided by I is equal to c by beta minus 1 e to the power minus ct, and I just write c by beta into 1 by I minus 1 into c by beta minus 1 e to the power minus ct. So c by beta into 1 by I equal to 1 plus minus 1 e to the power minus ct. So I get I equal to c by beta whole divided by 1 plus c by beta minus 1 e to the power minus ct, where your c is n plus 1 times beta minus alpha. So I will substitute this value now here and get them in the form it is equal to n plus 1 minus alpha by beta divided by 1 plus n plus 1 minus alpha by beta minus 1 e to the power minus n plus 1 times beta minus alpha into t. And I know that St is equal to n plus 1 minus it. So if I substitute this value and simplify, I will get this value to be n plus 1 into n plus 1 minus alpha by beta minus 1 e to the power minus n plus 1 times beta t, beta minus alpha into t plus alpha by beta. This whole thing is divided by 1 plus n plus 1 minus alpha by beta minus 1 e to the power minus n plus 1 times beta minus alpha into t. Now let's see what happens as your t becomes large. So as your t becomes large, this goes to 0, this part goes to 0, and you are left with your it goes to n plus 1 minus beta by divided by 1, and your st goes to, this part goes to 0, so you are left with alpha by beta, this part goes to 0, you are left with 1. Now when this will go to 0, this will only go to 0 when n plus 1 times beta minus alpha is positive. So this is the condition which need to be followed such that you get some finite value for this st and it as your n becomes large. So what does this mean? This means that a fraction of the susceptible person will be there which has not been infected, and a fraction of infected person that has recovered. So this is the fraction who has not been infected, and the same fraction is deleted from the infected part. So that fraction has not been infected at all. So this is the conclusion for this SIS model. Let's see how the model numerically behaves, for which we will be using this Microsoft Excel. So as you can see that I already have the equations here. So I take the initial value to be 2000 and the infected one is 1, your beta is 0.001 and this value of alpha is 0.4. So as usual, this is your 0, this value is 2000 and this value is 1. So let me first put this is equal to 0 plus 1, and let me drag this value. Next we calculate this Si, this is equal to S0 plus H, which is again a constant. So I put a dollar multiplied by beta with the negative sign multiplied by S0 into I0 plus alpha, which is again a constant, multiplied by I. Close, and we get this value. And your infected, this is equal to I0 plus H, which is a constant, multiplied by this particular thing. So beta, which is again a constant, multiplied by Si. So this is your S multiplied by I minus alpha times I. So now I drag these values, and let's plot this. I highlight using the shift key and the cursor. Go to insert, the chart, and this chart. This is SIS model. I don't like grid lines, so I will remove uncheck grid lines. I want the axis title. So this is again time. This is the population. And I will change this series 1 and series 2. Go to chart design, then select data, select series 1, edit. So this is susceptibles, and series 2, edit infected. So I get this chart for the SIS model. Now let's now go back to the slides. So our numerical solution to this SIS model shows that this value, this is the infected one and this is the susceptible one. So if you look into the solution, it says that as your T becomes large, your S is approaching alpha by beta, and your I is approaching n plus 1 minus alpha by beta. So, if I calculate my alpha by beta from here, that is 0.4 by 0.001, which is 400. So, you see that your susceptible alpha by beta, so this is reaching the value 400, and your I minus n plus 1 alpha minus beta will reach the value 1600 plus 1. So, which is approximately this particular value. So, the conclusion is that as your time increases, a fraction of the susceptible persons will be there, and in this case which is 400, and of the fraction which has not been infected is n plus 1 minus this alpha by beta, and due to which your infected person has only reached 1600 plus 1, which is this value. So, with this we go to the next model, which is called the SIR model. It is just an extension of the SIS model, but only with another compartment. So, there you have your rate of change of susceptibles. This is the infected, and this is called recovered. These three classes are there now. So, when the infected person comes in contact with a susceptible one, they infect that person, and hence this particular term comes here. The infection rate is beta. Now, from the infected class, some of the person gets recovered at a rate alpha, and since they move from this infected class to the recovered class. So, from that is why here it is minus alpha I, and it is added in the recovered class to plus alpha I. Now, from the recovered class, some people are also again susceptible. So, minus gamma R is going back to the susceptible class. So, we have now three class: susceptible, infected and recovered, and this is the dynamics between them. The initial condition is S0 is n, there is only one infected, and right now no recovered. We now look into the equilibrium solution of this SIR model, and as we know, we put ds dt equal to 0, di dt equal to 0 and dr dt equal to 0 to find the equilibrium solution. But before that, if I add ds dt plus di dt plus dr dt, I will see that this and this cancels, this and this cancels, and this and this cancels. So, basically this becomes equal to 0, and if I integrate that, I will get S plus I plus R equal to some constant. Now, initial condition, initially at t equal to 0, you have S0 equal to n, I0 equal to 1 and R0 equal to 0, which we get from here. So, if I substitute it here, I will get S0 plus I0 plus R0 equal to constant, and n plus 1 plus 0 is the value of the constant. So, I get a relation S plus I plus R, that is equal to n plus 1, which we will again also use to find the equilibrium solution. So, if I put these to be zeros, from here I get I. If I take common, then it is beta S minus alpha equal to 0. This will get alpha I equal to gamma R, and this will give minus beta S I plus gamma R equal to 0. Now, from here I will have I equal to 0 and S equal to alpha by beta. I name this as I star and S star. Now, if I equal to 0, it means there is no infections. I mean, none of the person is infectious. So, there is no point of studying this model, because if I put I equal to 0, the R is also 0 from this equation. So, we get some value of the susceptible and the no infectious, no recovery. There is no point of studying this equilibrium point. So, we will study where you have infectious people, where you have recovered people, and at the same time you have the susceptible one. So, you have this your S star, which is equal to alpha by beta. Now, if I put this value of S star here, I will get I plus R equal to N plus 1 minus S star. Because S plus I plus R is always constant and that value is N plus 1. So, this is true for any variable S, I and R. So, basically I get a relation I star plus R star is equal to N plus 1 minus S star, which is N plus 1 minus alpha by beta. Now, I will use this equation to get the value of I star and R star. So, if I replace the R star, I will get I star plus alpha by gamma I star, which is equal to N plus 1 minus alpha by beta. So, if I take I star common, I will get N plus 1 minus alpha by beta divided by 1 plus alpha by gamma. So, this is the value of I star, and for R star I will just have alpha by gamma into I star. So, it is alpha by gamma multiplied by N plus R minus alpha by gamma divided by 1 plus alpha by gamma. So, I get the value of S star, I star and R star, and this is the equilibrium point which we will study. If you want to look into the stability analysis, that is the linear stability analysis. So, you know you have to find the matrix A, where you differentiate this with respect to S, I and R, and the matrix which you will get is beta I star minus beta S star gamma, beta I star beta S star minus alpha 0 and 0 alpha minus gamma. So, I leave the stability analysis to you. This is the Jacobian matrix which you will get. You have to find the eigenvalues, you have to form the characteristic equation and use Routh-Hurwitz criteria to find the condition for stability. Now, what we look into is the numerical solution of this SIR model. So, I have this SIR model already typed. The initial condition is n, 1 and 0, where the value of n I have taken to be 2000, the initial value of infected is 1 and there is no recovery is 0. The value of beta, it is 0.001, h is 0.1, alpha is 0.4 and gamma is 0.01. So, with this we start with t equal to 0 and this is equal to 0 plus 1, and I will drag them later. So, this is equal to S0 plus h, which is a constant, so I put a dollar multiplied by this whole thing minus beta Si plus gamma R. So, minus beta multiplied by S multiplied by I. Since beta is a constant, I put a dollar plus gamma, which is 0.01 multiplied by R, which is 0. So this gamma is also a constant. So I put the dollar sign and add. So plus this minus 2 star. Now this is equal to I0 plus H which is a constant. So I put a dollar multiplied by this beta Si minus alpha I. So beta multiplied by S multiplied by I minus alpha, which is 0.4 multiplied by I. I have to put dollars in front of the constants. So this is a dollar, this is another dollar, this is beta Si minus alpha, so which is again a constant, and this value finally this is equal to R0 plus H, which is constant, multiplied by, so alpha I minus gamma R. So this is alpha multiplied by I minus gamma multiplied by R. So this alpha is a constant, I put a dollar, and this gamma is a constant. Okay, so the reason I already calculated is that here I just show the calculation, and here the correct one is already there. So you can just compare. So I now just drag to more than 300 values. And let me plot them. So I change the font size to 20. I just align them, and let's now plot the graphs. So in this case I have to take a little more values just to find the true dynamics of the model, and that is the reason that we have taken so many values. Okay, now I go to insert, I choose the graph, and I get the values. So I just change the color of this say let's make it green. Okay, and if you want to change the title, this is a SIR model. If you want to change the series, go to select data, go to edit, and first one is susceptible. The second one is infected, and the third one is recovered. So we get this dynamics. So one thing you need to know here, that our equilibrium point does not show any zero value, but you can see this curve has almost touched the x-axis, that is where the value is 0. But in reality that is not happening. What is happening is that if I see the last value of the infected, you can see that this is becoming less and less and less, and ultimately it is coming to 1, and slowly you will get a non-zero equilibrium value here. It is not actually going to 0, but the value is very, very less, and that is why this is infected one shows that there is a increase at some point and slowly the value goes down. It never goes to 0, it goes to some very small equilibrium value which is positive. The susceptible, as from the equilibrium solution, you will see reach certain equilibrium value non-zero, and so is the recovered class. Now, if you plot this figure by using this set of parameter values, I have taken again n initial value as 2000, 1 infected, no recovered, beta remains the same, alpha remains the same, gamma is also 0.01. So, you get this figure. So, your susceptible, as you can see, it is going to 0, but then a little increase, because some of the recovered will move back to the susceptible class. Your infected, there is an increase in the infection, but then it goes down, and then a part of the population, they have also recovered. So, this is a modification of the previous model, which is known as the SIR model. With this, we come to the end to the lecture of this epidemic models. In our next lecture, we will be talking about more interesting models. Till then, bye bye.